in this topic, topic 6, I want to look at some chemical reactions and also equations, very specifically what we call ionic equations, equations involving ions. I'd like to look at solubility, an ionic substance dissolving, and also precipitation, where the reverse occurs. And then I want to go on to have a look at some reactions of acids, a very particular type of cation is involved there, and I'll look at the reaction of acids with what we call active metals, with oxides, with hydroxides, and also with carbonates. And at all times then I'll write down the reactions by way of practice of writing chemical reactions. But first, let me remind you of the demonstration I did just a day or so ago, where I took water, I took some sodium chloride, some salt. I, on that occasion, used just some salt packets from the canteen. This lunchtime they saw me coming and chased me away, so I've got to use the real stuff here, sodium chloride. And if I dissolve that in water, it gives a clear solution, as you're familiar with, and then I can put in my electrical test probes and find that the solution conducts electricity. And I mentioned at the time when we were looking at ionic bonding, the reason for this was the ions were released into solution and they can then move and carry a current. What I didn't mention at the time was how is it that an ionic material such as sodium chloride, where we have a three-dimensional lattice of positively charged cations attracted electrostatically to negatively charged anions. This is a high melting material, it's a brittle material, it's a hard material. All that suggests there's strong ionic bonds, a strong force of attraction between these ions. How is it then that I can just break up this lattice just by stirring it in cold water? Well, it comes a little bit from the unique properties of water. I've mentioned also that a water molecule is not a symmetric shape, it's not a sort of a linear molecule, it's actually an angular shape, and this is crucial to its interaction with other matter. Okay, let's look a little bit more about water, and maybe I'll start off by just drawing up a water molecule including the angular shape. And if you remember from our electron dot diagrams, there were a couple of lone pairs of electrons associated with the oxygen, a couple of bond pairs associated with the OH bonds. Now, the electrons of the OH bond are not absolutely evenly shared between those two atoms. Why not? Well, oxygen has 8 protons in its nucleus, hydrogen has 1 proton in its nucleus. So an electron is, we might imagine, attracted more strongly towards an oxygen atom than it is towards a hydrogen atom. So the electron pair of this bond are piled up a little bit at the oxygen end. To use the scientific term, we say oxygen is more electronegative than hydrogen. The greater the electronegativity of an atom, the greater the tendency of that atom to draw electrons of a bond towards itself. Now, the net result of that is there's a little bit of a pile-up of electrons at the oxygen end of the molecule compared to the hydrogen end. And I might illustrate that with a delta minus at the oxygen end and a delta plus at the hydrogen end. And I'm using here a little delta, which in mathematics or in science in general means a very small bit. So a very small negative charge relative to a very small positive charge. This is nowhere near as big a charge as you get on a sodium cation or a chloride anion. Very small, and overall the water molecule is neutral. And I want to try and show you this in action. I have in this burette water. I've added actually some food dye so you can see it. Now, I might need the people towards the front to confirm what we're going to see. I'm going to put on my lab coat because the white shirt is probably not compatible with the blue coloured water. It's not a terribly dangerous liquid. I'll put on my blue safety glasses so as to be in total harmony here, and take a balloon. Now, what I want you to see is if I just open that, the water runs straight down into the tray. If I now put a bit of electricity, static electricity, on the balloon, you can see, if you're at the front, that that stream of water is curved. You're not convinced. I need a new balloon. How about, it might, I won't use the blue balloon, I'll use the yellow balloon. This demonstration is better done in the winter where I have a wool sweater that can really build up the static electricity. Probably doing terrible things to the microphone, but here we go, here we go. Let me put perhaps a new piece of paper there so you can see what's happening afresh. People at the front, can you see that the stream of water is actually being bent by the influence of the balloon? I've generated a charge on the balloon, and without touching the stream of water is attracted towards that charge. The explanation for this is that the water molecule is a polar molecule. It has one part of it that is relatively negative compared to another part. If I introduce a charged surface, I will get attraction between the water molecules and the charged surface. And this is what's happening when an ionic compound dissolves. You can imagine thousands upon thousands of water molecules in even a small amount of water. The relatively negative end of the water molecule will be attracted towards the positive sodium cations. And while the interaction between that partial positive charge and the full charge of the sodium plus cation is very, very small, providing I have lots of water, then the sum of the interactions will overcome the ionic bonding between the sodium ions and the chloride ions. Moreover, the relatively positive side of the water molecule will be attracted to the chloride ions. And overall, the sum of many interactions between water molecules and a chloride ion will give me a solution of salt or sodium chloride. So let's focus on just one chloride anion. I can imagine there to be multiple but very weak interactions between the relatively positive part of the water molecule and the negative anion, and similarly with the sodium cation, the water molecule can flip round the other way and solvate, or to use another term, aquate the ions. So overall, we can overcome the very strong attraction between oppositely charged ions using a solvent such as water, which is very polar, to use the jargon. Well, how do I write the equation for this? What we're doing is starting off with solid sodium chloride. We're ending up with the ions in solution, sodium ions and chloride ions, and we can prove that by electrical conductivity of the solution. I can indicate that we have a water solution by using AQ to indicate the state. AQ standing for equated or an aqueous solution of sodium ions and chloride ions. And this is an ionic equation. It involves the presence of ions. Let's look at another situation. Maybe I take an ionic solid, barium chloride. Barium's group 2, very bottom of it, forms Ba2 plus ions. And what I end up with is Cl minus in solution. And I have to be a little bit careful about how I represent that chloride part. It is wrong to represent it as Cl2, let's get the charges balanced up, 2 minus. That would suggest something that is a Cl2 unit which has an overall charge of 2 minus. That's not the case here. We happen to have 2 separate Cl minus ions. And now that we've actually separated the ions, we do indicate the charges here, while on the ionic compound itself, when they're combined in a solid, we don't indicate the charges. We can tell that this is a dissolution reaction or a dissolving in water reaction because the symbols AQ have appeared, and they're very specifically associated with reactions of materials dissolving in water. It's a common reaction. Water is literally the solvent of life. Okay, and we can write any of these equations in this sort of way. Now what I want to do is show you a reaction of this sort of thing. Show you some dissolving reactions, and let me take, for example, some water. And in one, I'm going to dissolve a compound lead nitrate. Oh, there's one large lump in here. Okay, now there we go. A bit more, there we go. Some is good, more is better. Lead nitrate, I'll put the formula on the board in one moment. Lead is very bottom of group 14. It's a metal. Top of group 14's carbons and non-metals, so we've got one of those groups that the nature of the elements change as we go down the group. In the other beaker I want to dissolve some sodium iodide. In both cases I'm starting off with a white powder. If I were to do the conductivity test, the solutions in both cases would conduct electricity. The reactions, the equations for the reactions that I've just done, in the first case, lead nitrate has this formula. Nitrate's a polyatomic ion. By that I mean I've got a collection of atoms, 1 nitrogen, 3 oxygens, held together by covalent bonds, all of which have a charge. And the NO3 ion has a 1 minus charge. So I need 2 of those to balance up the lead 2 plus. In the right-hand beaker, I end up with this occurring. Polyatomic ions, we give them a separate category because they hold together as an ion in solution. But exactly the same equation process, solvation process is occurring with the negative end of the water molecule, water dipole, being attracted to the lead ions, positive end to the nitrate ions. The other material I dissolved in the left-hand beaker was sodium iodide. To give me those ionic equations. Now, watch closely when I mix the two together. I get a pretty instant reaction, and what I see is yellow stuff, and it's gone opaque too. And what I've actually got is a yellow solid precipitated from this reaction. Now, if I filter this solid off, I have a filtering apparatus to hand. I'll set it up. It might take a little while to filter, but pour my yellow stuff in there. Check that I've put a beaker underneath. What I'm getting through is a clear solution. What I will show you in a few minutes is a filter paper in which there's a yellow solid. Some chemical reaction has occurred. What have I got in the solution? Well, I've got this collection of ions. We find that not all ionic material are soluble. How do we know which are soluble and how do we know which are not soluble? Well, in part, and certainly at first, it was done by experiment. So what I could do is experiment like that. I see a result, and then I want to identify or analyze the products. And as it happens, I have a sample here of something that says lead iodide, and if I put a sample of that out, you'll see that it's a yellow compound. So a good possibility for what I've made is lead iodide. Now, looking at the equations, there are just two possibilities of what could happen. I know that these compounds dissolve in water. So if I add one water solution to another, then I'm not going to suddenly get these popping out of water. And anyhow, I know that they were both white compounds. I know that ionic compounds must have a balance of charge, so that I can't have an ionic compound containing just lead 2+ and sodium plus. There'd be nothing to hold it together. So the two possible products would be one involving lead and iodide ions, or one involving sodium and nitrate ions. And I might go and get a jar of sodium nitrate, and I didn't manage to find one, and look at what sodium nitrate looks like, and if I managed to find one, it happened to be a white colour. So that's good evidence. The precipitate I got was lead iodide. Now, how is this? Oh, it's a little bit further to go. How do we know whether something is soluble or not? Well, at this stage, the easiest way to determine solubility is to look it up in a solubility table. And we've summarised that on page 10 of this topic as to what materials tend to be soluble and what tend to be insoluble. And it'll be a useful table to keep a note of when you're doing the tutorial this afternoon. So what you will see in the solubility table is, for example, that iodides are all soluble with the exception of lead iodide. That's the reaction we've had a look at. So, how do we represent it? Well, let me write down our starting materials in a chemical equation. I've got lead, I've got nitrate. Just for a moment, I'm not going to balance the equation. I'm just going to put what species are present. I've got sodium, I've got iodide. I get as my precipitate lead iodide, and from the charges I know that I've got to have 2 lots of iodide iron for every 1 lot of lead iron. In the solution that is coming through the bottom of the filter funnel, I still have sodium ions and nitrate ions. And if I wanted to, and maybe I'll set this going, what I can do is take that solution and boil off the water. This will take a while, so I will set it going and we'll come back to that later. Let me firstly swap that over. Leave that going. I have in solution then sodium ions and nitrate ions. If I remove that water, I will end up with sodium nitrate, and we'll see if we can get that. Meanwhile, this is, let me pour out just a little bit of the residual stuff there, and if I open up the filter paper, you'll see that I've got solid lead iodide. And we can use this sort of process to convert chemicals that we have into chemicals that we want, if they happen to be different things. Okay, so back to our chemical equations. I can see that from this equation, sodium ions and nitrate ions exist on both sides of the arrow. There's no change in their state or their presence there. And they are what we call spectator ions. And to be sort of a bit corny about it, spectators are not allowed on the field of play. So what we can do is cross off these spectator ions. And if I neaten up the equation and rewrite it, we will focus solely on what is changing. And in general, in chemical equations, that's the useful way to proceed, where we focus entirely on just what's changing. Now, I need to balance that up, so I'll put a 2 there. If we look back at our original mixture, you might not have realised it, but I actually used twice as much sodium iodide as I did lead nitrate. And as a consequence of that, the combination of ions was correct to optimize the amount of lead iodide I have. What I am doing in the beaker now on top of the Bunsen is taking what's left, which is the sodium ions, the spectator ions. And if I remove the water, I will end up with solid sodium nitrate. And we'll leave that going for the lecture. What we've looked at then is a precipitation reaction. I can recover the salt that is in solution by evaporation of the water. Now, the example of the precipitation reaction in the notes actually used silver and chloride, and that is, to my mind, not as spectacular because it's white. So I go from sort of white materials to other white materials. So I thought I'd show you this one as a different example. But what I'd like to do is go through the example 2 on the top of page 5 of topic 6, where the scenario that you're given is that water solutions of lead nitrate and sodium sulfate are mixed. What, if any, reaction occurs? The way I proceed with this is say, okay, the water solutions that I've got include lead nitrate, so I've got lead ions present, nitrate ions present, I have sodium ions present, and sulfate ions present. what, if any, reaction occurs? I firstly write down the ions. I identify two possible products, lead sulfate or sodium nitrate. I then go to my solubility table and find that all nitrates are soluble. So sodium nitrate's not going to precipitate from the reaction. And while almost all sulfates are soluble, we find that lead sulfate is one of those that is not soluble. So that I can now go back and write the ionic equation for what's occurring with lead ions reacting with sulfate ions, getting the ratio correct to precipitate lead sulfate. I can recognize this as a precipitation reaction because I'm going from ions that are AQ to a material that's a solid, S, in the equation. Okay, well, one other rather special cation is the H plus cation. And if I just remind you of the electron structure of a hydrogen atom. A hydrogen atom has one electron. There is one proton in the nucleus. It's atomic number 1. If by some means I remove that electron, I will end up with something that has no electrons associated with it, but one proton in the nucleus, and so overall I have a positive charge. And we call this the hydronium ion or hydroxonium ion, H+. It has an incredibly concentrated charge because I've got no electrons which create volume to the species. It can only exist in water solution. That only occurs because water is such a good solvating agent and the relatively negative end of the oxygen water molecule, oxygen part of the water molecule, then interacts with the H+. So in all cases, when we come across an H+ ion, it's always as an H+ AQ ion. It is what we'd refer to as an acid. There are a range of very common acids, excuse me. Nitric acid is one of them, and that in water generates H+ and the nitrate ion. Hydrochloric acid is another. HCl itself is a gaseous molecule, but in water it forms hydrochloric acid, in which it splits up entirely 100% to give H+ and Cl-. And another common acid is sulfuric acid, has the formula of H2SO4. It splits up into water, gives H+. Again, it actually gives HSO4- as well as SO4 2-. I've left it to last as it's a little bit more complicated. In most applications, we can think of H2SO4 splitting up 100% to give 2 lots of H+ and 1 lot of SO4 2-. But if I was to be rigorous about it, I would have a little bit of this present as well. And that's the proportions are difficult to portray in an equation like that. Many things react with acids, and I'd like to actually go through some of those things because it's a very important diagnostic tool. It's a very important way of dissolving materials. I think the best thing to do is if I demonstrate the particular reactions and then write them on the board. And the first reaction that I want to have a look at is a reaction of an acid with a reactive metal. Now, let's start off here. Let me put, for example, copper in one tube, and copper is actually a non-reactive metal. Sometimes we call them coinage metals, things like copper, silver, gold, platinum. They're non-reactive, and as a consequence of that, they are useful for applications such as water pipes, for jewellery. On the other hand, magnesium is classed as a reactive metal. Now, I haven't done this experiment with magnesium powder before, so not entirely sure what's going to happen. But let's add to that some hydrochloric acid. If I add hydrochloric acid to copper, nothing happens because it's a non-reactive metal. If I add an acid to a reactive metal, I get a gas produced, which is hydrogen gas, flammable gas, characteristic sort of squeaky pop. That's actually got really quite hot there, and if I keep on adding acid, oh dear, it's just steam you see giving off. If I keep on adding acid, I will dissolve all the magnesium metal. Let's just prove to you that it doesn't actually matter what acid I use. That was hydrochloric acid. Let me add some nitric acid to the magnesium metal. Same things occurring. Gas is given off. There's actually a little bit of a side reaction there involving the nitrate bit, which gives you the brown gas. Don't want to add too much of it because it doesn't smell very nice. What I get then is a reaction in which the metal dissolves, hydrogen gas is given off, and I end up with a hot solution which eventually will clear to will cool down to a clear solution. We're going to just put these over here a little bit out of the way, and right on the board the reaction of a reactive metal with an acid. Let's take magnesium solid. It's the H plus of the acid that is the reactive bit. I saw a reaction in both those tubes. H plus can only exist in aqueous solution. I end up by dissolving the magnesium to get magnesium 2 plus. There's water present, and hydrogen gas is given off. Now, if I was to balance this up, looking at the type of species on each side, it's balanced. Looking at the number of each type, I need to have a 2 there. So I now have 2 hydrogens on each side of the reaction. And with ionic equations, the third thing to check is that the charges are balanced on both sides of the reaction arrow. So overall I've got 2 plus on the left. Overall I've got 2 plus on the right of the equation. So that's a fully balanced ionic equation. Now, if I had used hydrochloric acid, then evaporated off the solution, I would have got magnesium chloride as the salt produced. If I had used, instead of hydrochloric acid, if I had used the nitric acid, and evaporated the solution, I would end up with magnesium nitrate as the salt that I generate. So that in the first place, in the dissolving reaction, it doesn't matter what source of H+ I use. If I wanted to then recover the salt I'd get would depend on the acid I got. So if I was to summarize what goes on, so an active metal plus H+ gives me a salt, and that's the code word for ionic compound, plus hydrogen gas. And that's a very, very general type of reaction. Now, I've lost my safety glasses. There we go. What I want to look at is the next type of reaction, and I want to start to look at the reaction of acid with a variety of compounds. And the first one I will look at is the reaction of an acid with an oxide, and for the oxide I'm going to use magnesium oxide. Now, magnesium oxide is in this case a white powder. Magnesium oxide doesn't dissolve. Well, let's see what happens with water. Magnesium oxide doesn't dissolve in water. If, on the other hand, I now add some acid, let's take hydrochloric acid, and stir. I find that I am going from a cloudy solution where the fine powdery magnesium oxide was dispersed through the water but remained as a solid, now to a clear solution where the magnesium oxide has actually dissolved. Now, how do I know whether a chemical reaction has occurred or not? And I'd like to try and draw a slight difference, or draw the difference, which is quite a subtle one, between something like sodium chloride dissolving in water to give sodium ions and chloride ions, and there I've just got a dissolution reaction with no change in the nature of the ions. In this case, and we could only prove it by further analysis, in this case, when the magnesium oxide dissolves, it's not just dissolving to give magnesium ions and oxide ions, but is actually reacting with the H+ to form something else. I can suppose that something's happening in that when I take magnesium oxide in just water, no reaction occurs. All acids are mostly water, but the difference is they've got H+ and some counterion. Now when I add the acid, reaction occurs. So what's actually happening in this case? Well, let me take calcium oxide, solid, and I'm going to write out two equations actually. I'm going to start off by writing out the ionic equation where calcium oxide reacts with water to give calcium ions in solution and actually more water. And let me just stop my Bunsen burner because it's sort of hissing and spitting over here. And what I've ended up with, it's hissing and spitting even more over here, what I have ended up with is a solid. Now that solid looks a little bit yellow, which is a slight worry, but actually that's because the lead iodide is not 100% insoluble. So there were a few lead ions and iodide ions that combine to give a little bit of lead iodide. The vast majority of that solid, however, is the sodium nitrate, now that I've got rid of all the water. Okay, back to my reaction of acid with an oxide. I end up with dissolving the oxide, releasing the metal as a cation. The oxygen ends up as water. I've indicated that as L for liquid. It's sort of a little bit of a tautology, a repetition. If I put H2O, AQ, so conventionally we put it as liquid, I balance the equation by saying I need 2 lots of H plus for every oxide present. And that would be the ionic equation for my reaction. Depending on the acid I use, depends on the salt that I'd get if I went on and did the second stage of evaporating the water. And I could write what I might call a formula equation. And I'm now going to leave out the state symbols for a reason I'll tell you in a moment, illustrating that if I use hydrochloric acid, I will end up with calcium chloride as the salt and water. And I need to balance that with 2 lots of HCl. Now, this actually is useful in that it tells me I need 2 lots of HCl for every 1 lot of calcium oxide. It may be useful if I was interested not so much in the dissolving reaction, but changing the calcium oxide into, let's say, calcium chloride. If I use a different acid, I'll get a different salt. I don't add the state symbols, the solid, liquid, gas, AQ symbols, because HCl AQ actually has no meaning. It is an expression that you often see in textbooks, and it's wrong. HCl AQ suggests, in a literal sense, that you've got HCl molecules floating around in water solution. That's not the case, because as soon as you take HCl gas, add it to water, you break the bond and you get 100% H plus and Cl minus. So it's nonsense to say HCl AQ. And as a consequence, for the formula equation, I am showing you the bulk of what's happening and not focusing on some of the detail as we have done with the ionic equation. So with an oxide plus an acid, we get a salt plus water. And I can do the same sort of reaction with a hydroxide. Let me take calcium hydroxide. Again, a disappointingly white compound. It doesn't dissolve in water. If I now add my acid, it's a bit of bubbling there. I need to explain that, but I'll explain that after the next reaction. I'll just check that I got the right bottle, yes. It has happened. Some is good, more is better. So I end up with a clear solution. The ionic compound has completely dissolved. 2 things are actually going on here, a side reaction and a primary reaction. I want to focus on the primary reaction. We find that all hydroxides will react with acid to dissolve, and if I look at this case that we've just experimented with, calcium hydroxide, solid plus H plus AQ. You know something's happened because the solution's gone clear. The calcium ions are released into solution. The hydroxide combines with H plus to give water. If I was to balance this up, I need to check that I've got the same type of atoms, the same number of each type, and charge is balanced. I need 2 lots of that. I'll end up with 2 lots of water. If I use hydrochloric acid, and I did, and then evaporated the solution, I would get calcium chloride produced. So in the same way that an oxide plus acid gives salt plus water, a hydroxide plus an acid gives a salt plus water. But what are those bubbles? Well, they're actually a little bit of contamination, and I will return to those in one moment after I've shown you the third and final of these reactions. And that's the reaction of a carbonate, and we'll stick with calcium, and I'm going to use calcium carbonate, effectively powdered limestone here. Calcium carbonate, limestone, doesn't dissolve in water. Again, that familiar white slurry. If I add to that some acid, I get some bubbles. I better just check that those bubbles are not hydrogen gas. In fact, they put out the match very, very quickly. It doesn't support combustion. The gas that's produced in this case is carbon dioxide. You can see that very quickly I've gone to a clear solution there, and the equation for what's going on is analogous to the ones I've looked at here. Except for a tiny bit more complicated. So calcium carbonate plus H plus gives us a calcium ions in solution, and we end up with carbon dioxide gas and water as a byproduct. Why is that? I can balance that equation by putting 2 lots of H plus there, and then the charges are balanced left and right. Imagine this broken into 2 parts. Imagine the H plus reacting with a CO3 2 minus, and I'm going to write it with the cation first, followed by the anion. They give you something called carbonic acid, H2CO3. However, that's not particularly stable and decomposes into carbon dioxide and water. And if I look at what atoms are involved, I can see that I get H2O and CO2 from that. So it's quite a good diagnostic test. If I've got a material which I think might be a carbonate and I add acid, I get bubbles coming out of the solution, and I test those bubbles and they don't support combustion, then the chances are I've got a carbonate, the gas produces carbon dioxide. Carbon dioxide is used in fire extinguishers because it doesn't support combustion. Let's go back to this oxide case, just as a little bit of a diversion. What's happening there is that there's, particularly in an old sample of hydroxide, there is some carbonate present. All hydroxides can absorb carbon dioxide from the atmosphere and produce carbonates, can produce actually something called a hydrogen carbonate, which is similar to this, and it's that contaminant, that hydrogen carbonate, that gives us carbon dioxide, bubbles out of solution when I add the acid. Okay, so to summarize what we've looked at today, some ionic materials will dissolve in water. Water is a remarkable solvent because it has the ability to rip apart a strongly held together ionic lattice. It does that by many interactions between the polar ends of water, either the delta plus or the delta minus parts of the water, and the cations or anions of the opposite charge to the interacting end of the water molecule. Not all ionic materials, however, do dissolve in water. There are solubility tables that we can look up to check whether something dissolves or not. If I mix together ions from two solutions that will produce an ionic material that doesn't dissolve, then I end up with a precipitate. And I can use this to synthesize different chemical compounds. The ions left in solution can be reformed into an ionic solid by evaporation of the water. One cation, which we'll study at length next week, is the H+ cation. That is the active part of acids. An acid such as hydrochloric acid or sulfuric acid produces H+ in water solution. It's only in water that this cation can exist. It's quite reactive. It can react with some metals, in fact many metals. It can react with oxides. It's a good way of dissolving what is otherwise an insoluble oxide. It can react with hydroxides, dissolving them to produce water and the metal ion. It can react with carbonates, dissolving them, producing carbon dioxide and water. If anyone has ever cleaned off some bricks, old bricks that have mortar on it, you can buy in the hardware shop muric acid, which is the same as hydrochloric acid. Sometimes it's marketed as just brick cleaner. It dissolves the lime that's in the mortar, and you end up cleaning up the bricks so that you can reuse them again because it dissolves carbonates. Okay, I'll leave it at that.